All right, so if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. These are the words of Niels Bohr, who we see here in this picture, one of the founding fathers of quantum mechanics. We see him in this picture together with Albert Einstein. So Einstein himself actually had was so profoundly shocked by this new theory of nature that he actually had a hard time even just accepting this new theory, even though he was also one of the founding fathers of quantum mechanics. But shocking as it is, we now know that quantum mechanics is the most precise theory of nature ever invented. So one of the more interesting questions which were asked in the last couple of decades was, can we use this? Can we take advantage of this new quantum world, and can we make it work for us? And more precisely, can we build computers that are based on this new theory of quantum mechanics? And can they perform any better than classical computers, regular computers? So you might have heard about quantum computing. It's been in the news quite often recently, with many of the tech giants introducing their latest developments in the field, their latest quantum processors, their actual cloud platforms that you can access these days quantum computers through the cloud, and you can actually run quantum algorithms on these computers. There's a very small prototypes yet. They cannot do anything useful yet, but this is pretty cool. And you might have heard about this term, the race for quantum supremacy. So quantum supremacy would be the first demonstration that a quantum computer, a real quantum computer in the lab, can perform some tasks faster than any other classical computer that we have on Earth. So still, this is not going to be a useful task, but this is a proof of concept, and this is expected actually to happen this year. So this is very exciting. So quantum computing is generating all these buzz and a lot of news, and the reason, of course, why it's so interesting to so many people and companies is this great computational power that these computers are expected to offer us. So this is a very short talk, so I won't have too much time to go too deeply into many of the aspects of quantum computing. I don't think I'll have time to tell you where we're at with quantum computing and what sort of problems we want to solve in the near future. Because what I want to do is I want to actually try to give you a little bit of an intuition on how these computers actually work, how they are different than classical computers, and how these differences may allow them to perform some better in information processing, okay? And I think that these intuitions and also a little bit of the jargon on the field will allow some of you to go back and then read more about quantum computing and learn more about where we're at today and what sort of problems these computers are expected to solve, and if it's, might be of use to your field or just interesting in general. Okay, so this is going to be more of a scientific kind of a talk, okay? Okay, so before we talk about quantum computers, we need to talk a little bit about classical computers and how they work. So classical computers on a fundamental level have two basic building blocks. We have the bits, of course. This is how we store information on a classical computer. So a bit is just a system that has two states. We usually call them 0 and 1. And this strange notation there is just how physicists denote states, okay? So in the computer we have many ways to implement bits. For example, we have many tiny electrical wires, and each tiny wire can either be at 0 volts or at 5 volts. And this is how we physically implement a bit, for example. So these are the bits. This is how we store information. We can take many bits and store a lot of information. And then the second building block for computers is the gates. Okay, so a gate is a device that takes some input bits and then performs some function on them and then gives us output, some new output bits, okay? So this is, for example, the NAND gate. This is the function that it performs on the input bits. And the NAND gate is actually an example for a universal gate, which means that we can perform with a bunch of NAND gate, we can perform any function on any number of classical bits. So we can take now a bunch of classical bits, which have many states, and we can start manipulating them now to go from one state to another and to another using these gate operations. And this is basically a computer. A classical computer is this machine that has many bits, which means that it has many different states, all the different combinations of zeros and ones, and it just goes from one state to another and to another according to some program, according to how we decided to wire all these gate operations. Okay, and then it reaches at the end some final state, which is the result of some meaningful calculation. Okay, quantum computers replace this notion of a bit with the notion of a quantum bit, or in short, a qubit. And this goes like this. So while the bit is restricted to being either 0 or 1 at every point in time, the quantum bit or the qubit can be in both 0 and 1 at the same time. Okay, we call it the superposition principle. This is kind of like the famous Schrödinger cat, right? Being both dead and alive. So qubits can really be in both 0 and 1, but in fact, and more precisely, it's not that they can be in both 0 and 1 at the same time. They can be in superpositions, in a linear combination of 0 and 1. We write it like this: alpha 0 times the 0 state plus alpha 1 times the 1 state, where these alphas, these coefficients, are actually, they're called the amplitudes, and they're actually complex numbers. This is important. This is really the heart of quantum mechanics, that we have complex numbers as coefficients of these superposition states. All right, so this is the qubit, and there is a way to write it in terms of vectors, so we can just write the amplitudes as a tiny complex vector, and there is a rule that says that these vectors must be normalized, and so quantum states in the quantum world are represented by normalized complex vectors. Okay, I was told that everyone should be convenient with linear algebra here, so we're going to do a little bit of linear algebra. Okay, but another way, more geometrical way to kind of visualize these qubits is in terms of a vector on a sphere. So you can think about a three-dimensional sphere, and then the qubit state is represented by the point to which the vector points. Okay, and we can see that this is really a generalization of the bit, right? The bit is either 0 or 1, either the south pole or the north pole. We can think about one of two basis vectors, 1, 0, and 0, 1, and then the qubit is a linear combination of these two basis vectors, again, with complex coefficients. Okay, now just like in classical computers, we had the notion of a gate that processes these bits, that manipulates the state of classical bits. In quantum computing also, we have quantum gates to process quantum information. So a quantum gate manipulates the state of qubits. So for example, this is a single qubit gate, which means that it takes a single qubit and it transforms its state from one vector to another vector. And these single qubit gates are represented by unitary matrices. Okay, these are 2 by 2 unitary matrices. Unitary matrices are just matrices that preserve the norm of a vector. Okay, so these are the transformations. Now, so this is an example for a very famous gate in quantum computer, a Hadamard gate. It's represented by this matrix. And these are single qubit gates. Now, we also have 2 qubit gates, which are gates that operate on 2 qubits. Okay, so the state of 2 qubits is given by a 4-dimensional vector. Okay, so this is because if we have 2 qubits, we have 4 different states, right? 0, 0, 0, 1, 1, 0, and 1, 1. But in the quantum world, we can be in a superposition of all of those. So we have a four different amplitudes, 4 numbers to denote the state. And then the gate operation would be represented by a 4 by 4 unitary matrix. Okay. All right, so and by the way, this vector grows very, very quickly with the number of qubits. It grows as 2 to the number of qubits, right? Because the more qubits we have, the more states we have, and we can be in all of the states at the same time in the superposition. So the length of this vector is exponential in the number of qubits. So just think about the fact that a quantum system with 300 qubits, yeah, must be represented by 2 to the 300 different complex numbers, which is larger than the number of atoms in the universe. Okay, so the amount of information that we have in a small quantum system is gigantic. Okay, and finally, to complete the analogy with classical computers, here we also have the notion of a universal set of gates. So this means that with a small number of quantum gate operations, actually 3 single qubit gates and 1 2-qubit gate, we can perform any manipulation on any number of quantum bits, which means that we can take a bunch of qubits, yeah, represented by this gigantic 2 to the n size vector, and we can perform any manipulation, any unitary transformation to take it to a different gigantic vector using only 4 tiny gate operations. Okay, and then we can build a quantum computer, which is simply a system that has many, many, many qubits, and it just goes from one superposition of states to another superposition of states to another superposition of states according to some gate program, okay, according to how we operate with these quantum gates. All right, and this is a very nice picture, right, because it shows how much more powerful the quantum computer is, right, while the classical computer can only, go through one of these computational paths, a single classical computational path. The quantum computer can sort of scan all the computational paths in parallel. Okay, now this is where usually popular talks about quantum computing end, with this nice picture saying that quantum computers can do parallel computation, but there is actually a very difficult problem with this, okay? And you can kind of see it also from this picture, because you see that at the end of this process we also end up with all of the results in parallel, right? All of the we end up with a superposition of results. And this gets even worse because when we decide to look at the computer, to measure the computer, we can only get a single answer. This is called the collapse of the wave functions. Physicists call it the collapse of the wave function. And in fact, we don't even have a way in advance to predict which result we're going to get. Okay, so this looks pretty bad for quantum computers. But there is a way around this. I won't go into too much of the details, but as I said, I want to give you the intuition for this. So if we look at the quantum algorithm as a series of these unitary matrices operating on these vectors, going from one superposition to another, we will see that each path, each classical path that the quantum computer takes is assigned a complex number at the end of the process. For example, this red path over there is assigned a complex number, alpha gamma, and then the other red path leading to the same computational result is also assigned another complex number, beta delta star here. And because these are complex numbers, as I said, this is the most important thing, they can cancel each other out, right? They are complex numbers, they have magnitude and direction, so they can, for example, these two red paths leading to the first result can cancel each other out and give us 0 probability to measure this result, while the other two red paths leading to the second computational result may interfere to give us a perfect probability to measure the result. And so this is really the power of a quantum computer. This is called interference, where different computational paths leading to the same result can interfere constructively or destructively to cancel out the bad results to the problem or amplify the right result to the problem. So now I don't have any more time, actually. I have half a minute left. And with this, I want to just tell you a little bit of an intuition to what sort of problems we can solve using these interference and using these superposition states. There is a way to look at the same quantum algorithms a little bit differently, as if we are generating a potential landscape for these qubits, and the qubits will always look for the lowest energy spot in the potential landscape. Now, classically, so we can start with some potential landscape where we know the solution, we know where the qubit will sit, but then we can change the potential. Classically, as we change the potential, the ball will remain in the left valley. But quantumly, as we change the potential, when the two valleys reach the same potential level, the qubit will actually go into a superposition. This is kind of like performing the Hadamard gate, which I told you about before, on the qubit. And then as we continue to change the potential, the qubit will choose to be in the lowest energy state. And this kind of shows you a little bit of an intuition how this may be related to neural networks and optimization of neural networks. And finally, there is also the concept of a quantum neural network, which means that I don't only optimize the network using quantum algorithms, but I also create a network which is by itself quantum. So you can think about a neural network which is in all the different possible states, meaning all the different possible parameters. So with this, let me thank you. And if you do want to know a little bit more about where quantum computing is now and what we do at QM Quantum Machines, you're very welcome to contact me personally. Just replace the info@quantum by Yonatan@quantum, and I'll be more than happy to talk to you.